The formal part of any science class I've ever taught always starts in that same place, with measurement and the standardization of units. The reason for this is at the heart of science is that it's an empirical endeavor. That means we only study that which can be measured and observed. And if we only study that which is measurable, then we better have a fairly sophisticated way to standardize the units with which we measure. However, what we find when we look at the history of this process is that the standardization of units is fairly elusive, and we've been through multiple iterations. Most recently in May of 2019, when a fairly significant part of what many of you will recognize as the metric system, though it has a slightly different name now, undertook a new revolution in the way we standardize units. We'll get to that in a second. Where I like to start when I talk about measurement is here, Boston, Massachusetts. And I like to look at the Harvard Bridge, which spans the Charles River and connects Cambridge to Boston proper. Cambridge is where you will find some of the more recognizable colleges in the area of Boston, Harvard, and the Massachusetts Institute of Technology. The latter there is where we turn our attention, where a fraternity of MIT, Lambda Chi Alpha, took one of its fraternity pledges, Oliver R. Smoot. And in 1958, in what can only be described as an odd prank, but the people at MIT are a little different. They rolled Oliver Smoot head to toe down the bridge and measured the bridge in Smoots. As a side note, before we leave this map, if you wander off to the top corner here, you're going to find an area called the North End. And it's where you'll find one of the better pastry shops in the country. If you ever visit Boston, you probably ought to go there and get a cannoli. But the interesting thing about this is that the Smoot has stuck. And if you go to the Harvard Bridge today, you will find every 10 Smoots down the bridge, a set of markings which label off the Smoots and measure the bridge from one end to the other. And what's even more interesting is that these have become so integrated with the city of Boston that they will often be used in formal documents. If you, for instance, get in a car accident on that bridge and an officer comes to write up the report for that accident, they will often write down what Smoot on the bridge the accident happened. And so you have this rather obscure measurement that's not really used anywhere else, although in earlier editions of Google Maps, apparently you could measure things in Smoots, but a recent update has took that away to much dissatisfaction here. But that this unit, which is fairly obscure, has worked its way into, at least in this region, something fairly recognizable. And again, if you go to the bridge now, you'll find in 2008 a plaque was set into the bridge so that every time you walk this bridge, you can see the reference to this event. So this happened on the 50th anniversary. And what they found when they rolled Oliver Smoot down this bridge is that this bridge is 364.4 Smoots, plus or minus 1 ear, because it's fairly important that you maintain measurements of uncertainty when you measure things. A Smoot is equal to 5 foot 7 inches, but it turns out this is not a very good way to standardize measurement, because you can no longer use Oliver Smoot. Although he's still alive, he's almost certainly not the same height that he was when he was rolled down that bridge, and he certainly is not the same height in the evening as he is in the morning, because we all in fact shrink a bit over the day. So we run into a measurement standardization problem here, but to that we will return. When we talk about measurements in this class, it is fairly important that you understand that a measurement includes two things. That is a number and a unit. If you leave off the unit, you leave off the coding for that information. And that unit says a lot about that measurement, and they cannot be taken for granted. A simple and nearly ridiculous example of this is to ask you what is bigger, 1,000 or 400. Probably sensing the trick, you would be somewhat hesitant to respond until I give you some units. And now I think you would probably almost certainly want the 400 over the 1,000, and if that is not your preference, then I would like to do business with you. The system we're talking about here, though, and specifically that we'll use primarily, although not exclusively in this class, is the SI units. It refers to the international system of units. You might ask, if it's the international system, then why is it abbreviated SI? And that is because officially, internationally, it's referred to as Système International d'Unité, or the System International Units. And it is inverted because it is a French derivation. And in Romance languages, you typically, but not always, put your adjective after your noun. And so that international is referring to the systems. They refer to it as SI and not IS. It is a revised version of the metric system. It was originally established in 1960. The metric system, though, dates back all the way to the 1700s and was an effort by a number of European scientists, but spearheaded by a guy by the name of Antoine Laurent Lavoisier, who we'll come back to as we talk about various other aspects of science. It is it is built, I should say, around 7 base units, and these units have to be defined or standardized. And we'll come back to that in later videos. All other units are referred to as derived units, and derived units are combinations of the 7 base units. And then everything in the SI system is set up in conversion factors of base 10. So this is your king, Henry died drinking chocolate milk. These are the 7 base units in the SI system. You should definitely write these down. You should underline them. You should circle them. Stars, arrows, exclamation points, whatever you need to do to write down that you need to know and be able to reference these 7 base units. The entire system of measurement, everything we measure, from the diameter of a cell to the speed of a comet to the size of a galaxy, all of that stuff can be measured somehow, some way, using these 7 units. We have length measured in meters. We have mass in kilograms. This is a slight deviation from the metric system. And the metric system was originally in grams. When we converted to SI, grams are a fairly tiny unit of mass. So the kilogram gives us a slightly bigger standard. Temperature, rather than being in Celsius, is in degrees Kelvin, or I should just say Kelvin because you don't refer to them as degrees. There's no degree symbol there anyway in the measurement. We'll talk about those a little more in some other chapters as well. Time is measured in seconds. Amounts are measured in what's called a mole, and the official abbreviation for a mole is in fact MOL. A mole is a counting number. So it's very similar to like a dozen stands for 12. A mole stands for a specific number of particles, and it's usually used to count atoms, subatomic particles, that kind of thing. Electric current is measured in amperes, so as in a circuit, and luminosity, or the brightness of a light source, is measured in candelas. These are the 7 base units in the SI system. Anything else that you want to measure is some combination of those. There are a number of combined units that we'll use both in this class and you'll use as you move into other areas of science. But for instance, if we take length and we multiply length by itself 3 times, length times width times height, you get volume, which is a formula you should be familiar with. If we take length and combine it with time, and not just time once, but time squared, or meters per second squared, you get what's referred to as acceleration. How much is your speed in meters per second increasing for every second that you travel, hence the seconds squared. Mass over volume is density. That is a combined unit. These are all combined units that we use, but they don't have special symbols. A number of combined units that are used in the SI system get their own symbol, several of which we'll talk about over the course of the year, but an example here is force. Force is generally described in physics as mass times acceleration. So we already saw that acceleration was meters per second squared. Mass is measured in kilograms. So a unit of force in the SI system is kilogram meters per second squared, which is a bit of a mouthful. So we typically use the name Newton to stand for, as in Isaac Newton, to stand for that kilogram meter per second squared. So the symbol for force in the SI system is the capital N. And then, of course, as we said, the SI system is broken down into factors of 10 in its prefixes. And so all conversion factors go base 10. We're going to spend most of our time living here: kilograms, centimeters, millimeters, milliseconds, that kind of thing. Your data packet has a list of these prefixes. So you don't need to have them memorized, you just need to know how to use them when we move on to talk about conversion factors. So that's it for the introduction here. Our next video, we're going to talk about how we go about standardizing those base units.